right, so this is just some review stuff. Hopefully these aren't super hard. They should be straightforward, but it's just there's always, you never know who has gaps or who was like, who practiced these a lot or who had them explained poorly, and then there's always playing catch up. It's just if it's old news, then that's great, but if it's something that you I don't know, if you don't already understand these really well, it's good to not just be able to use these, but actually sort of understand where they're coming from, because some of these are pretty straightforward. And in the very near future, we're going to talk about the mirror image of these, which is like logarithms. So it's the exact same identities, but for every exponential identity, there's a logarithm identity where you just take everything and you do it inside out and backwards, and it's squaring is a lot simpler than taking a square root. Same idea. So it's really, really important that you understand what x squared is before you understand what a square root is. And same thing with exponentials and logarithms. So here we are only talking about exponents. It should be pretty straightforward. There are some very concrete, some very solid reasons for these identities, but if you've never thought about it before, this is a good time to take a step back and sort of think about some of the why, and then we can just start jumping into the problems. So let's just start with the basics. Originally we think of the exponent. We think of exponents as being positive whole numbers. So a to the m is however many there are. There are m copies of a, and you multiply them all out. And so that's that's sort of a definition. If you want to ask yourself, what does it mean to have a to the 0, and what does it mean to have a to a negative number? Well, we'll see that there are some various reasons that the answer to those questions, there are very good reasons why those answers to those questions should be something in particular. But let's talk about some things that we can learn right away even if we only think about whole number exponents just for the moment. What else can we think about? So for example, well, for this one, a to the m times a to the n, let's pick a specific example. Let's just pick let's make 2 cubed times 2 to the 4th. So why not? Okay, so we've got 3 copies of 2 all multiplied together, and then we've got 4 more copies of 2. So what ends up happening? Well, so that's 1, 2, 3, and then 4, 5, 6, 7. So we have we're literally, how many copies do we have? We add up how many copies there are. So 2 cubed times 2 to the 4th. There's 2 to the 3 plus 4 power, because there's this many copies times of 2 times 4 copies of 2. So that's literally the idea. So it's just you do this m times, and then you do it another n times, and it's the same as how many a's did you multiply together. Well, you have you write down A, M times N many times, and you multiply that many copies of A. So you start with A, then you multiply by an additional A all the way until you've got M plus N copies of A written down on the board. And by our definition, that's just this many times this many is that many multiplied. So that's basically it. So this, I don't know, maybe it's been a long time, but this should have been fairly early on. As soon as you start learning about exponential notation, this should have been one of the first things that they sort of had you think about. But it's a good food for thought that, if you've never done it before, any time, as soon as possible is a good time for that. So that's one identity. That's leave room for a few more. So so I encourage you to kind of do that. Anytime you think you see something and you're like, oh, there's probably an identity for that, well, just follow the same pattern but use different numbers, or just use very specific numbers that aren't too big, and just write down what actually happens, and then what the thing that ends up happening will sort of shape what the identity actually is. So for example, what is the other one that you see sometimes? Well, what is this? Well, it's the trouble is at the moment I've got 3 different numbers and they're just all completely general. To see the kind of what is the pattern, what does it look like? Well, what if I have 3 squared to the, I guess, yeah, that's okay, I guess. That's kind of, it's gonna be a somewhat large number, but what actually ends up happening? Well, what we really want to know is, first of all, we know that we're starting with 3, and then we're multiplying a bunch of 3s, and then we're multiplying a bunch. Now we're multiplying a bunch of. Since we expanded that, we're multiplying a bunch of 3 times 3. So at the end of the day, we're gonna have a bunch of 3s. So this is 2 3s to the 4th power. So here we go. Let's figure out how many 3s we've got. So that's really so this one's a little bit more abstract because it's like we're taking it to the next level. So it's not just a power of 3 times a power of 3. We've got a power of a power. So that's a little bit wild, but we've got 2 3s, and we've got how many copies of 2 3s? We've got 2 3s, but then we've got a total of 4 we've got 4 copies of 2 3s multiplied, so we've got a total of 8. So we've actually got 3 to the we've got 2 of them here, we've got 2 here, 2 here, another 2 here. We've got a total of 8 3s multiplied out. And that's actually kind of the general pattern. You've got so if you wanted to sort of say what this looks like in general, this becomes very hard to write down, but it's like how many A's do you have? You have M A's, but then you have M A's again, and then how many times do you have M A's? You've got M A's in different times. So you've got A to the M, then you've got this thing on the left, when you write it out, it looks like this. You've got a to the m, but you don't just have one copy of a to the m. You've got a lot of a's. So you've got m copies of a, but then you've got n copies of that m copies of a. So you've got this many times, and then you do it that many times, and that's how many times you multiply a. So you got a multiplied m times n times. So that's a lot of multiplying. So what do you get? We end up getting this. So that one, so that one's maybe takes the same idea as one step further. So if you're ever in doubt, just try out with some exponents like maybe 5 to the 2 to the third or something like that. You'll see pretty quickly just by writing down just count how many copies are you writing down, and if your identity is getting it correct, then you know that you haven't accidentally remembered the wrong thing. The patterns should sort of, in generality, it can be hard to think about it in the abstract, but once you start picking some sort of smaller whole numbers and start sort of understanding the pattern, you'll probably you'll convince yourself that that's basically how it always works. So that's so those are the two kind of the most fundamental things about exponents. So let's think about that for a minute. I need to make some room here. We're going to push this a little bit farther now. So now what we would like to do is, does it make sense to allow exponents to be negative numbers? Well, maybe, we've seen this already and we should be used to it somewhat, but let's take a minute to just step back and really sort of really make sure that this makes sense and we really believe that these things are what they should be. Okay, so yeah, the first time you see this, just sort of in the general history of mathematics, and as a single person's development as someone who studies math, this is kind of the order that you're introduced to this as a person. So both as just historically, what did people understand and accept about these, and then once society has these notions, how understand explaining them to a young person, we do it in roughly the same order. So originally we have originally we have an idea about a to the m, where a is bigger than 0, m. Okay, so if I call these identities 1 and 2, number 1 especially, so it turns out that identity 1 kind of goes a very long way to sort of telling us, well, what should happen if we allow negative exponents. And there's more than one way to think about it, but no matter, if you want negative exponents to make sense, few different ways of thinking about it, but kind of the answer you end up getting for how this should work should be kind of the same. If you want to keep what you already have working without any disruption. So if we want to allow negative exponents, well, identity 1 is very close to our hearts, as like that's one of the first things that we learn about exponential notation. What happens when you multiply two different powers of the same base? How do you combine those? What do you get? Well, one thing that's sort of interesting is well, let's look at 0 first. So 0 is always kind of a little bit something you have to stop and think about. So negative exponents are an issue, and then what about 0? Well, if I have a to the 0 times a to a to the first, for example. Well, what we just said is that our favorite identity says that this is a to the 0 plus 1, which is a to the first. So if we just divide by a on both sides, we get 1 is equal to a to the 0. That's kind of we didn't, this would work even if no matter which a bigger than 0 we picked here. If we picked a equals 2, for example, we could do the same demonstration. So it's kind of, if we like identity number 1, then we probably want to say that if the base is 0, then everything gets really, really messed up. It's like we're dividing by 0. But the rest of the time it should be fine. Okay. And then you can ask similar questions about negative exponents. So what about negative exponents? So what would that do? Well, what would it have to mean for a to the minus m? What would that have to be? Well, we just sort of convinced ourselves that we just convinced ourselves of this, right? Well, we just convinced ourselves that a to the 0 has to be 1, and if you're not convinced, you should probably pause and take a few minutes and rewatch the section right before, or maybe just sort of think about it for yourself. But once you're convinced that a to the 0 has to be 1, well, the negative exponents is like somehow they're canceling because you add the exponents. We like this identity, so if we want this identity, if we want to extend our definition of a to the m so that it includes negative exponents as well, then we want it to get along with our favorite identity, which would mean we have, this is what ends up happening. If a to the minus m makes sense, and if we can just add the exponents, we get a to the minus m times a to the m is a to the 0. A to the 0 is 1. Okay, so then if I divide both sides by a to the m, then a to the minus m must always be the reciprocal of a to the m. So that's kind of like a definition. So I mean, this is it's short computation, but it's a very theoretical computation, kind of very important. It's something that's really, really valuable to sort of think about. It's kind of the really, the why of the way that things are in mathematics. And the last thing that I want to remind you about uh, is for these last two, it turns out that things can get really weird if a is allowed to be negative. Fractional exponents, you might already know the answer to what these are, but let's talk about it from the point of view of these identities. We really like these identities. But for these last two identities, let's just start with a to the 1 over m. And for this very last identity, its identity number 2 is what's going to be, maybe I can call this identities 3 and 4. So this identity 5 is basically related to identity number 2. Okay, so for, make sure I get this as dry as I can, or else it's just going to be a waste of all our time trying to write on a wet board. Okay, so I'm assuming that the base is bigger than 0, or else weird things can happen, and who knows. Well, let's just sort of explore. Let's try to understand this by applying. If we do this, now suddenly one of our identities. We want to use identity number 2 because that's how we can cancel out that denominator. We want to multiply 2 fractions in the exponent. So identity number 2 is what's going to help us out here. So we just multiply those 2 exponents, and what happens in the exponent? The exponent is 1, so it's just a. So what we have is and on the other hand, this is that sort of familiar. We have another thing that kind of plays the same role in mathematics and arithmetic, and that is, well, it's whatever a to the 1 over m is. It's when I raise it to the nth power, I just get a. Well, the thing that does that job is the positive nth root of a. So if m is even, maybe there's a positive and a negative nth root, but the positive nth root is what we use the radical notation for. And so for convenience, we use and actually, because radicals are so annoying to write, sometimes just using exponential notation with the fractional exponent might just be easier to write down just in your word processor. So it's just, after a certain point, everyone's equally comfortable with both, and it's just a matter of style points, or just sort of, it's just a stylistic thing. You want to be really comfortable with using both of those completely interchangeably. I mean, in some situations, there might be some really subtle difference where one version is easier to read than the other, and it's just it's kind of like a little matter of emphasis. The more comfortable you get with this, the better. then sort of finally, well, what would a to the, well, what if it's not just 1 over n? What does a to the m over n mean? Well, that would be the same as, if we want identity number 2, well, that's m times 1 over n. Well, I can write it as 2 steps. Let's do that. You know, either way that you want to do it is there's also there's 2 ways to look at this. You could do it the other way around as well. You could put, well, I put the 1 over n on the inside, but I could have done it just equally well like this. So it's either way, you take the nth root and you take the nth power, and it turns out you can do those in kind of, this m looks like an n, but because I didn't draw it very well. 2 ways of saying the same thing, as long as you're taking the positive nth root and a is a positive number. These are all completely equal to each other. So equal to, either you do the nth power and then take the nth root, or you can take the nth root and then take the mth power of the whole thing. And it's kind of the fact that the order you do that in doesn't matter is the same as saying that the order that you multiply m times 1 over n, which one comes first, that also doesn't matter. So those are the definitions. So now it might be a good time to pause. If you want to take an overview of that, I'm going to leave that in the upper right corner. I'm going to erase these proofs, and I'll just do a couple very quick examples. I mean, even if you're already comfortable with these, I hope that thinking about why they should be true and how just these 2 things right here, these 2 observations are really, really nice and kind of inform how we want to, everybody sort of agrees that that identities 1 and 2 are just really, really good and should sort of inform the way that we think about exponents kind of in general. It would just be if we're in some mathematics where we have to give that up, then that's some foreign landscape that's bizarre and unusual, and it's not somewhere that we want to be right now. So we like these, and then what does that tell us? It tells us we get all of this as soon as we have that. So that's pretty cool. All right, so let's just do some examples. So I don't know, maybe I'll do 7. Seven to the something, right? A 7 to the something. So what do I have here? So maybe 49 times 7 to the 3x times all right, so yeah, so why not? let me add one more identity to the list. It's very much related to this one here. But if I have a to the m minus n, then this is it's basically this because it's like a to the m plus negative n. So right, that this is identity number 1, and then identity number 4 says that so this is kind of the proof. So what is a to the m minus n? Well, it's a to the m times a to the negative n, but a to the negative n means you take the reciprocal of that one. So times the reciprocal is what we're using here. So we've got, well, we want to write these all as powers of 7, and that's not too bad. So that's 7 squared times 7 to the 3x times 7 to the 1/2 and we've got yeah, I'll write it this way. Basically, if it's in the denominator, I can flip it to the numerator by number 4, but I have to take the negative of the exponent. So this last one, I'm dividing by a to some power, but then I can write this as you just take the negative of that exponent. So anything that's in the denominator, you write that as 7 into some power, but then you flip it to the numerator by taking the negative of that exponent. So dividing by 7 to the 2y minus 1 is the same as multiplying by 7 to the negative of 2y minus 1. So 7 squared, 7 to the 3x, 7 to the 1/2. So positive 1, but then minus 2y. So 3.5, like I said, would be 7/2. So 3.5 copies multiplied out. So I did all of these. There's the 3x, and then okay, so that's just something that just to show that it's possible, a good exercise for just juggling. It's just if in some situations weird things might happen and stuff might cancel and you might get something better. In this case, it's just an exercise to make sure that we are comfortable with this sort of exponential stuff. I think that's about as much time as I wanted to spend on that. It's there, it should be kind of old news, but I wanted to look at it from a theoretical perspective. But then, the exercises, what do you end up doing with it? Looks kind of like this. All right, so if there are more questions, you can ask about it, and maybe we'll come back to it later. But that's about what I wanted to say about it.